Good evening. Welcome back to AP Stats Notes Online. I'm going to wrap up Chapter 6 tonight talking about geometric random variables. We've been talking about binomial random variables. You have to understand when the binomial setting is satisfied, checking your bins, binary independent, the number of trials are set, and the probability of success is the same each time you perform a trial. Geometric random variables, or the geometric setting, is a lot of the same thing. So we're still going to take a look at outcomes that are, or events that are binary, and we know what that means now. Two possible outcomes. Okay. We still want each of our events to be independent, and we still want the success rate to be the same. The difference here is we don't know the number of trials going into it. Instead, we're going to count the number of trials it takes to get what we want. Okay? And so it leads to a new acronym that you hear a lot. Instead of bins, we can stop and check to see the bits, right? For any of you Bridget Jones fans out there, the wobbly bits, right? And if it fits the wobbly bits, then it's going to be a geometric random variable, okay? So still, again, the bottom line here is geometric and binomial are exactly the same, except for in binomial, we know the number of trials we have. Geometric, we're counting the number of trials. We ought to finish this up until a first success, right? So instead of rolling a pair of dice 4 times and counting the number of doubles you get, the binomial example of that would be rolling a pair of dice until you get a double, right? So an example here would be rolling 2 dice until a double shows up. And we're going to count the number of trials it takes to get there. Okay? So if a situation fits the geometric setting, then we can use a geometric random variable to list or to describe the possible outcomes. Okay? So it's the same thing, right? We're counting the number of trials. So your success, so if I'm going to define, if x is a geometric random variable, then what can happen? Well, x, the first success can happen on the first trial, or it can happen on the second trial, or the third, or the fourth. And thinking in terms of rolling 2 dice, when might we get the first double? We could get on the first roll, the second roll, the third roll, the fourth roll. So since we're still counting, this is still a discrete random variable. All of our possible values are whole numbers with gaps in between. The difference is, when is this going to stop? Am I guaranteed to get doubles on the 5th roll, the 6th roll, the 7th roll? When am I guaranteed to get a double? And the answer to that question is we're not. So this could go all the way out to infinity, right? There's an infinite number of values that x could take in a geometric setting. As we're going to keep performing trials until we get our first success, and we don't know when that's going to happen, right? Now, each outcome still comes with its own probability, so we could do a distribution. Only problem is we'd never be able to finish it because, like I said, the possible values are going to go all the way out to infinity. Okay, so those are your possible values. For that same reason, coming up with the mean of a geometric random variable becomes really tough also. For a discrete random variable, we know we'd take the value times the probability for each value and then add all those up. The problem is our values don't stop. And so we're never going to know when to stop doing that process. So the discussion about finding the mean of a geometric random variable is going to be very, very short, and we're not going to worry about where it comes from because of that reason. Okay, we'll get to that in a second. All right, so that's the deal with the geometric. We're counting trials until we get a success. For example, if we are playing Monopoly, right? One way to get out of jail is to roll doubles. That's one way to get in jail too. Right? Doubles is a good thing in Monopoly as long as you don't get 3 in a row. If you get 3 in a row, you go to jail. Once you're in jail, you instead of waiting a number of terms to get out or having a get out of jail free card or whatever, you can roll the dice, and if you get a doubles while you're in jail, then you can get out. We know from before that rolling a doubles, the probability of rolling a doubles on any roll is 1/6. And we can go through how to get that. If you need to, let me know, and I'll be more than happy to show you where that comes from. But just for now, that's the probability of getting doubles. So if we're going to talk about, suppose that a player has to stay in jail until he or she rolls a doubles. There's no rule about the number of turns you have to wait, or there's no get out of jail free card. You have to keep rolling until you get a doubles. The probability of rolling doubles is 1 in 6. Explain why this is a geometric setting. Well, on each roll, what's going to happen? If you're in jail, what do you care about? Well, you're either going to get a doubles or you're not, right? So this is still binary, because we're talking about doubles or not. Each roll is independent. We're talking about dice here, right? And the success rate stays the same. It's 1/6 every time. It's 1/6 each time you roll the dice. Now, do we know how many turns, how many rolls it's going to take to get our doubles? Do we know how many rolls we're going to do going into trying to get out of jail? The answer to that question is no, we don't. We're just going to keep rolling until we get doubles. So we're actually going to, the number of trials is not set. We're going to count the number of trials until we get doubles. So it satisfies our wobbly bits. And so this is a geometric setting. Okay? Part B, define the geometric random variable and state its distribution. Okay? Well, we can do that. All right, so it satisfies the geometric setting. We're going to define the geometric random variable by this, right? We can let x be the number of trials until a doubles, right? State its distribution is kind of a weird way of saying this, but what that means is, okay, I know that x is going to take on different values, right? It might happen on the first roll, the second roll, the third roll, all the way out to who knows when, okay? So when we talk about stating its distribution, then we need to have the probability, and that's really the only parameter that we need. So in this case, x is the number of trials until it doubles. It's a geometric random variable. Its distribution is basically all of these values, and the probability of a success every time you do a trial is 1 in 6. That's enough for that. Letter C says, find the probability that it takes exactly 3 rolls to get out of jail. Let's think about how we would do that, right? I want to know the probability of getting 3 rolls. How would I find this probability right here? Well, think about it. In order to get doubles on the third roll, right, what has to happen on the first 2 rolls? Well, the first roll will have to be not a doubles, right? No doubles in the first roll. And then, again, I'm not getting a doubles until the third roll, so that means the second roll has to be not a doubles, right? That means the third roll has to be your doubles. So let's think about that. What's the probability of not getting a double? If the probability of getting a double is 1 in 6, the probability of not getting a double is 5/6. And so it would be the same for the second roll, 5/6 chance of not getting a double. And then you're going to actually get a doubles the third time, that probability is 1 in 6. So since these are all independent, and these guys have to happen together to get your doubles on the third roll, we're just going to multiply these guys together. So in other words, to find this probability, I would take 5/6 squared, right? 5/6 times 5/6 times 1/6. And pay a little bit of attention about this exponent and this number. See if you can't see a pattern here. But so 5/6 squared turns into 25 over 36 times 1 over 6. This becomes 25 over, what, 6, 3, 8, 216. And you can divide that out. Okay? All right, now, letter D. I'm going to change this up a little bit. I'm not going to worry about the probability that it takes more than 3 rolls. Okay? Let's change this up and say, how about we find the probability that it takes, instead of 3 rolls, how about it takes 4 rolls to get out of jail? Right? And this is going to be a pretty quick conversation because hopefully you're going to see the pattern here. So if it takes 4 rolls to get out of jail, what has to happen? Well, I had to get a no doubles on my first 3 rolls, and then I get my doubles on the 4th. So again, the probability of no doubles is 5 and 6. So all these are going to be 5 and 6, and the probability of getting doubles is 1 and 6. Well, look what happens. When I multiply all these 3 together, I end up with 5/6 to the 3rd power times 1/6. Okay? And again, pay attention to this exponent versus the number of successes you want. 1 less here. So we go 3 minus 1, and that becomes the exponent on your failure rate. 1 less here becomes the exponent on your failure rate. And that should make enough sense. If I'm going to count to a particular trial to get my first success, that means all the trials that came first had to be a failure. And they're going to be independent, otherwise we wouldn't be talking about a geometric setting. So in general, how can you calculate geometric probabilities? The pattern looks something like this. If I'm going to count to the kth trial to get my first success, that means all the trials leading up to the kth trial had to be a failure. So I'm going to take my failure rate and raise it to the k minus 1 power. And then I'm going to have to multiply by the success rate because my process won't end until I get a success. So the very last term out here has to be the failure rate, right? And we can kind of put this to the test, right? What's the probability of getting doubles in the first roll, right? It's taking me 1 roll to get doubles. Well, I can go the failure rate, 5/6 to the 1 minus 1 power, but then I'm going to have to get a success, right? 1 minus 1 is 0, so this becomes 5/6 to the 0 power. This is 1. It goes away. It's just 1/6, which should make sense. What's the probability of me getting doubles on that first roll? Well, it's just the probability of getting doubles, which is 1 in 6. So we get to this pattern, and that's how we're going to find our geometric probabilities. Take the failure rate to the 1 less the number of successes that we're counting to, power, and then multiply by the success rate. That's the only way that our process ends is by getting a success. So let's use that. Okay? All right. Now we can go back up to what D says here. And if you mark that out, that's okay, but I'm going to go ahead and show you this. Find the probability that it takes more than 3 rolls to get out of jail. Okay? Probability that it takes more than 3 rolls to get out of jail. Well, we just taught, I'll talk to you a little bit about, we did this with our binomial setting, and we want to do this with the geometric setting. All right. What are all the possible outcomes of it taking more than 3 rolls to get your doubles? Well, it could be 4, 5, 6, 7, 8, 9, 10 rolls. You get all the way up to an infinite number of rolls before you get your doubles. So finding the probability of this becomes too tough. It's impossible. So what we do instead is look at it from a complement standpoint. This probability is the same thing as taking the complement and subtracting it from 1. What's the complement of it taking more than 3 rolls? Well, this is more than 3 rolls to get your first doubles. Well, the complement of that is that it takes 2 or less, right? So I want to find the probability of x being less than or equal to 2. Well, how would that happen? How would we get doubles on trials less than or equal to 2? Well, it might happen on the first roll, or it might happen on the second roll, and it would satisfy both of those situations. Okay? Well, we can use the formula here, 1 minus, okay, probability of getting success on the very first roll. It's just your probability of success, 1 in 6. We just talked about that. What about the probability of your success happening on the second roll? Well, what had to happen? I had to fail the first time, so 5/6, and then I had to succeed the second time, so that's times 1/6, and we'd go do that math. Okay? So that's how we would go about finding the probability of it taking more than 3 rolls. This is our complement. We subtract it from 1, and we'll be good to go. Okay, and again, you can type that in. I don't want to insult your intelligence. You can type that in and get that probability. Okay. Next question. On average, how many rolls would it take to escape jail in Monopoly? And that's what I was talking about before. Ideally, we would list out the probability distribution, multiply each value times its probability, and add all those up, and that would give me my average, my mean. But that's too hard in a geometric setting because we don't know when the number of trials will end. It could take an infinite number of trials to get your first success. So, how do you do this? How do you calculate the mean of a geometric distribution? This mean right here is just going to be 1 over p. Okay? It's just 1 over your success rate. Okay? So, on average, how many rolls should it take to escape jail in Monopoly? Well, on average, it should take you 1 over 6. That's your success rate. Now, how do you simplify this? You can't have a fraction in the denominator. You multiply it by its reciprocal. You get 6 times 1, and this becomes 6. So it should take you 6 rolls on average to get your doubles and get out of jail. Okay? So the next question, what is the probability that it takes longer than average to escape jail? Longer than average would be x is greater than or equal to 6. Or it just says longer than, so I guess it'd just be greater than 6. Okay? Well, again, greater than 6 is too hard to do because you never know when you're going to stop. So do the complement of 1 minus the probability that x is less than or equal to 5. That's the complement. So technically, you'd want to do 1 minus the probability of x being equal to 1 plus the probability of x being equal to 2 all the way out to the probability of x equaling 5, and you'd be done. And that's exactly how you want to show your work. 1 minus. Right? So this would be 1/6 plus, right, 5/6 to the first times 1/6 if we're using the formula, plus dot, 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 5/6 to the what power? The 4th power times your success rate 1/6, and that's how we're going to show work. But that's not how we're going to do it. Okay? What we're going to do, and I'm going to ignore this last question about the shape of the distribution. If we need to talk about it later, we can. I'm going to take the time now to show you how to do this in your calculator. Okay? So if you take a look in your calculators, binom CDF, binom PDF are in that distribution window. So is Geomet. So in your calculator, turn this light off. If you go to second vars, where your distribution menu is, there's your normal stuff, there's your binomial stuff, and here's your geometric stuff. And again, you see the 2 options, PDF and CDF, and those 2 work exactly the same way it does in binom PDF and binom CDF. Okay? In other words, before I get into this, I'll go back into here. Okay? If you're going to use your calculator, Geomet PDF and Geomet CDF are the same deal. This is for x being equal to k, and this is for x being less than or equal to k. Okay? It works the exact same way. Now, the difference here is that Geomet PDF, right, it still wants your success rate and the number of trials it takes to get to a success. But since we don't know the number of trials it will take, we can't put in n. There's not going to be an n here. So we skip n, we just put the success rate in, and we talk about how many trials we want to count to get the first success. It's okay. So those are the parameters that you'd put in, p comma k for both of them, right? So if I want to find the probability that x is less than or equal to 5, that's going to be geomet CDF. So I'll go back to the calculator here. That's going to be geomet CDF. Okay? It wants the success rate. Want to get a doubles, it's 1 in 6. And the number of trials you're counting until your first success. Well, that's 5. Okay? You get that. Now, that's just the probability of getting x is less than or equal to 5. We want the probability of it taking us more than 6 rolls to get a doubles. So this is the complement of what we want. So we got to subtract from 1. And so the probability of it taking us more than 6 rolls, more than the average number of rolls to get a doubles is 0.402. Okay? So this probability turns into 0.402. Okay? And that's how you use your calculator to get all your geometric probabilities. Now you still need to show your work, and your work shown would look something like this. Okay? Use your ellipsis if you need to, but you need to write out the first term, the last term of the range you need to find, and then use your ellipsis. So we guys still show our work. It's just the same as it was for the binomial stuff. But use your calculator to make your life a whole lot easier. All right? That's all there is to the geometric stuff. So that's it for Chapter 6. Homework's in the text. Have a good night. We'll see you guys tomorrow.